Okay guys, let's look at these, see how you did. First one, products of the acid-base reaction. What's the most acidic H on the board? Right here, the phenol. Okay? Yeah?
Yeah.
Most basic atom on the board? It's nitrogen right here. Yeah? Acid-base reaction, lone pair takes the H, electrons move on to oxygen, becomes a third lone pair, that's a minus charge, nitrogen binds to H. How we do? Question?
Why is that oxygen more acidic than the other OH when there's that, it can conjugate, can't it? Some of its lone pairs with the double bond in the...
Yeah, the resulting anion is conjugated, that's why it's more stable.
Oh, and it's negative, okay.
What do you mean conjugated? This oxygen is not conjugated. Where would you rather make a minus atom? This oxygen or this oxygen? This one, why?
Because it's conjugated, it has more places to go.
There's a p orbital next door. The new lone pair can now be in a p orbital interacting with the next door. Yeah? Uh-huh. Look at list of pKa's in the back with explanations. We have a phenol, pK of about 8 to 10, and alcohol is more like what? 16. Down below, about 16. Okay. Here's your relative trends. This explains why these are up here more acidic than down here. Down here, no resonance stabilization. Okay. Common pKa's, many things to learn there. You'll see those functional groups throughout organic 1 and organic 2. Okay? The explanation is over here. I would start at the top, the most acidic. It explains why it's most acidic. As you go down, it will explain why these are less acidic. Or the only thing it has going for it. The only thing this has going for it is hybridization effect. Effects up there are more effects, or they're more important effects. That's what you should take from that. Okay, this would be in the B, both of these in the B form, right? 7 and 10, or both below 12. Amino group, S minus, how do we do?
Yeah. Yes.
Yeah? Good? SH compound, yeah?
Yes.
5, C greater than A. C is the most basic, yeah?
Yes.
Then A, then B is the least basic. Newman projection, as drawn, it's this. The bromine and the isopropyl are the biggest groups right now. They're gauche. I rotated the front to make the bromine and isopropyl anti. And did I get it right? I did it pretty quick.
No, I think the hydrogen is supposed to be on the other side than the ethyl on the other side. Could you have hydrogen on the same side? Does it matter?
No, I think he's right.
No,
You're
he's
right.
right.
Over here, with the F straight down, the bromine is which way?
To the right.
It's bolded. That means it's coming towards you. If I'm over here, you're to my right. F straight down, bromine to the right. F straight down, bromine to the right. Going back on carbon 1 is an H. It's to my left. Front is correct. Back carbon, isopropyl straight up. Yes. Ethyl is going back. It's to my left if I'm over here. Is the ethyl going left?
Yes.
Correct. The H is coming forward. This looks good. I rotated just the front. I moved the bromine here. That put the F here and the H here. Looks good to me.
Wait, that's what I got to for the back chain. I got hydrogen on this side. That's what I got to, but for the back chain, I got hydrogen on the left side.
H here, ethyl here.
Yes.
How about when you originally drew it? Before you rotated?
The bromine was up top, hydrogen, fluorine, then... Okay, I see the issue.
You got it?
Okay.
If you're over there and the ethyl's going back, if I'm over here and the ethyl's going back, back is to my left. Why am I over here? Because I'm looking down 1, 2. 1, 2. If I'm over here, I'm looking down 2, 1. 2, 1. Looking down means 1 is here and 2. I'm looking down the road. I'm over here and down the road is going away from me. 1, 2 is away. That's why I'm over there. Dashed in bold. Up here looking down the board. The F and the isopropyl are on the board. The bromine is forward, that ethyl is back. So those are to the side if I'm over here. I'm just drawing what I'm doing. Okay, is it the third one?
Yeah, that's what I got.
Yes. Okay. I'll post these. I decided to do a little bit here. Instead of an answer key, instead of a video key. Although I can add, is the video key useful? Okay, I did that here because this was an ungraded quiz. You had it in front of you. I thought we'd talk about it real quick. And you can ask questions. Okay, so hopefully that was helpful. See where you're at. We go live on Wednesday, yeah? That's on Wednesday. We need to finish up today. We'll be beginning test 2 material on Monday. Okay, guys.
We stressed out so bad on the second presentation. That was great.
Maybe we can redraw some up here. Let's move ahead. We need to finish up this handout. This side is the sister trans. H is up here. The H is down here. These are what? Those are trans. How about here? The H is down. The H is down. Those are. The H is where here? That's an up carbon. That's an up carbon. It's already up. The other bond here is. Those are what? Trans. Okay. What's the relationship between the isopropyl and the F? These two groups are what? Yeah, those are cis. How about the F and the Br? What's their relationship? Trans. Those are trans. How about the Br and the isopropyl? Yes, those are trans. If we drew this in a perspective drawing, perspective is when we do dashed and bold. Do not use dashed and bold in the chair confirmations. You don't need it. And if you use it, you're doing something that's not needed and that's wrong. Not only is it not needed, it's just very not needed. It's not helpful. Okay, cyclohexane. We can draw a flat ring, commonly known on the board. We know it's really this chair conformation for reasons we said. Okay. Again, we can end up with drawing a right hand, but the real answer was a left hand. As long as we have thumbs, okay, if you draw a hand and you got the pinky over here next to the thumb, you're going to be wrong. But at this point, if you draw either one, you're right. All right, so let's just say, I'm going to put the bromine here. Now, it's tetrahedral carbons. We already got two in the plane. We got to then put one forward and one back. I'm going to put the bromine. It don't matter at this point. How about that? Now it matters. Because now the F goes where? We can't put the F here, because that would be 1, 2. This is a 1, 3 relationship. The F goes where? The third. Here or here? I'm not going to worry about it. Hands. Let's put it here. I'm going to do dashed or bold. Dashed. Because they're trans to each other. We want to make sure they're trans in our perspective. Where do we put the isopropyl? On the fourth. Here. Not there, nowhere else. How do we put it?
Dash.
The F and the isopropyl are cis, so we want it to also be like this. Boom, boom. Yeah? Now guess what? We could have also have drawn it like this. I could have put the bromine here, could have put the F like this, and I could have put the isopropyl like that.
Question.
And these both have the same relative positioning, relative stereochemistry. But these are stereoisomers, though. What type of stereoisomers are they? Well, we haven't got there yet. They're stereoisomers. They have the same connectivity. Okay. This is a right and left hand. Either of these answers would be acceptable for test 1. When we get to test 2, we have to understand that only one of these is right for that. The one that is right would be bromine forward. I think this is the actual correct one, but I will accept this on test 1. It has the correct relative orientation of the groups. Everybody with me? Questions about this? So understanding cis-trans, going between a chair conformation and more of a standard perspective drawing. And getting positioning right. Common mistakes here. Bromine here, and for some reason the F is here. And here it would be a 1-2 relationship, but the original was a 1-3. So how did that happen? It's wrong. We're drawing the same exact compound, just in a different way. And of course, not recognizing that these two groups are cis, and so over here you have the F forward and maybe F back. That would be wrong. Okay. Now we ended making a comment, I think, on Wednesday, which is the best positioning in chair conformations. Biggest groups prefer to be what? Equatorial has more room. Equatorial. I'm going to stick a group on here. Here's some group. And there's the ring, and then here's some bigger group. Right now, that group is equatorial. Straight down. If I set that down, that group would not touch the that bond would not touch the table. Okay. We've got 3 straight down. That has more room over there. If I do a ring flip, now it becomes axial, and we need to do this. This group now interacts with these 2 H's over here. They're also axial. 1, 2, 3. That's called 1-3 diaxial interactions. And that's sterics. Sterics is where bonds and atoms crowd each other. Instead, it's going to do a ring flip. And that group will move equatorial. Equatorial has more room. We really did not draw a ring flip on Wednesday. We need to do that. It shows ring flips here. Here it's axial. Here it's equatorial. The equilibrium can be measured, and it's known to be 18-1. This is preferred 18 times more because the methyl, the bigger group, is equatorial. Has more room. And so the electrons on the skin of that methyl group have more room to be electrons, and they're not crowded to other electrons. If we go to a tert-butyl group, which is bigger, the ratio becomes 4,800 to 1. This tert-butyl group really wants to be equatorial. Because it's so much bigger, it's like, I got to have my room. And I'm not going to do a ring flip. If we have two groups, then we say, well, which one would prefer to be equatorial? The bigger one, right? And so, which one's going to be favored at equilibrium? Which conformer? This one here, tert-butyl equatorial. Okay. But really, again, we'll go back and do ring flip, but let's keep going here. Let's do these problems here. So we'll kind of just focus on problems. Okay. Show the following in lowest conformation, lowest energy conformation. How many groups are equatorial in the best conformation? We're going kind of the opposite way. Previously, we went from a chair to perspective. Now we're starting with perspective. We've been going to go to chair. Okay, chair. Two offset horizontal lines. Connect with a point. Connect with a point. I can start anywhere. I can put the first atom anywhere. I like to start top right corner. I also see that bromine is bigger than F. So I'm going to start by putting a bromine equatorial. And I like to draw in the H's on the carbon with the substituents. It helps me orient things and make sure I'm drawing things correctly. Because these are up carbons, they get straight up bonds. And these three are down carbons, they get straight down bonds. So, well, which bromine is that? I'm not going to worry about right hand, left hand. I'm going to call that bromine the middle one. I just feel like I want to do that. Since that's the middle one, I can put the next bromine right next door. Is the next bromine going to be axial or equatorial?
Axial.
Well, there's cis, right? For it to be cis, and this needs to be axial.
I thought that made them trans if they were different.
No, that's not how you determine cis or trans. Common mistake. That's not how you do it. How do you do it? Why are these two cis? They're cis. They should be cis, right? We see it easily
Right.
there. Why are these cis over here? Because they're both what?
Now,
Well, I would say they're both below the H. Right? That is how you do it. Has nothing to do with both being axial or both being equatorial. That is.
Below their H's.
And that is one reason I like to draw in the H's and ask you to do it. Okay? Where do you want to put the F? We can still put it either way. I mean, we can still consider it. It depends on which bromine you consider that. If I want that to be the little one, where's the F need to go? Here. Should the F be... Now that's a straight down bond, and then the equatorial would be more like that. There are the four bonds, or two. Is the F axial or equatorial here? It's trans to that bromine. Trans would be...
Above the
The F is above the H, the bromine is below the H. Those are trans. There you go. Bromine, bromine, F. Bromine, bromine, F. Why don't we do ring flip here? I could have did it at the very beginning with just all H's. It may actually be more informative to do it here. Question?
Can we have the bromines on top of the hydrogen and chlorine on bottom? Can we do that?
Yes, that would be like drawing a different hand. Yes. And that would be okay. Just like over there, we did two. And then I checked one and said that's the actually correct one. Yes. Let's do a so-called ring flip. Because these guys can, and here we go. We got a chair conformation. Three straight down. Here, I'm going to change this white to here. We got a white and a red. Okay, let's get it straight. Three straight down, three up. One of the reds is straight up. The red is axial, and the white is what? Equatorial, because the other one is straight down. Yes. Whenever you do a ring flip, one end flips up, and the other end flips down. And when you do that, what happens to the red and the white? They switch positions. Now the white is axial and the red is equatorial. I'll do it the other way again. White axial, red equatorial. White straight up, red around the equator. This end, and it doesn't matter which end. I could turn it and do this end. If you move one end up, it doesn't matter which end. Here, let's move this end up, and this end down, the opposite end down. Now the red is axial and the white is equatorial. Ring flip moves axial to equatorial. All right? Right here, we'll see that. Right now the bromine is obviously equatorial. And the F is also equatorial. Wait a minute. Why are they both equatorial? I thought it was trans. You see, that has nothing to do with each other. Nothing to do with each other. Ring flip, we're going to pull this end down and we're going to pull this end up. Okay? I don't have the model, exact model, but we're pulling this end down and we're moving this end up. Let's do it on the board though. Okay, when I drew this one, which is the most common that I'll draw, I do two lines like that, right? To do the other one, we want to do two lines the other way. It's going to kind of mirror. And now connect this to this, and this to this. And I'm not as good at drawing this because I don't do it as often. This end, okay, we start this carbon is now here. That end got pulled down. And this end goes up, and that's there. Now, the atoms are still there. The bromine is still here, but the bromine is now axial. And the H is equatorial. Here's what is always the same. The bromine is below the H. It's still below the H. That will never change if it's the same compound. Now the other bromine is here. Now that's a straight up bond. And the straight up is going to be H. And then this is like that. The F is here, right? So that's a straight up, and that is a here. Where do we draw the F? Well, it's the same here. It should be above the H. It should be above the H. But you see that over here the F was equatorial, but now it's what? All halogens have switched positions between axial and equatorial. And these are the same compounds. These are in equilibrium like shown with those examples. The question is, which side of the equilibrium is favored? And the answer is the one that has the largest group's equatorial. Which one is that? Look at the bromines. One's equatorial, one's axial. One's equatorial, one's axial. That ain't going to give you your answer. That's the so-called wash. It's the same in both. Let's look at the F then. And which one is the F equatorial? First one. This is your best confirmation. And it just happens to be the one I started with. I could have drawn the not so good one first. I was not, it was a 50-50 chance for me. I was not looking at anything. It just ended up being the first one. What we could have done is we could have said, hey, if I do a ring flip, you just look at this. If I do a ring flip, these are just going to flip, and it will be the same, essentially. One axial, one equatorial, one axial, one equatorial. But, if I do a ring flip here, this is going to go axial. Well, that won't be as good as this. So you don't even really have to draw that if you just think that way. But if you end up this being wrong, then you're going to have to redraw it. Okay, so that's the so-called ring flip. There's some tricks where you don't always have to ring flip, but I don't want to take the time to tell you that right now because we're pushing the clock. It also, again, has to do with if you're allowed to draw either hand. Once we get to having to do one hand and be correct there, then you need to do ring flip. If you don't have to worry about hand, there's a kind of a trick, but I don't want to teach you that trick because I'm teaching you to avoid this. So, in any event, let's move to the next one. How about trying the next one on your own? Lowest energy confirmation. See if you can get to the answer kind of as quick as possible. The more you understand it, then you can kind of get quicker to the answer. Question? No. Here? Which BR?
Like on the other one?
This BR?
No, like on the next one, like the
This-
BR and the F. When you flip it.
You're talking about this program.
No, the other one. What was that running?
This one. Right now it's axial. When you do a ring flip, it goes equatorial. What do you mean top or bottom? It's below the H, yes. The bromine is below the H, right? But it's still below the H. You think it should now be above the H?
I did. I was just.
The bromine is not going to magically be above the H. That would be a different compound. Okay?
I was just thinking that the whole is not just like the that's why I was confused.
No, when we say ring flip, we're putting one up and one down. That's called a ring flip. It's not doing this. That's see here, this went up. Okay?
I understand that.
Okay. I'm just trying to figure out.
Thank you.
You say you understand. I just want to be. I want to be convinced you understand. Because a lot of times someone will say they understand and they
But I
really.
was thinking like the whole ring.
But again, we're up against the clock. That's where I come back and forth at you. Okay? Because just because I don't like it when you say understand, I'm like I don't think you understand. That's what I'm saying in my mind. I don't want to. But we don't always have time to do that. So what I ask is, think about it, and if you want to ask later, we can come back to it. Question?
Also, a reset on that first structure with the bromine, both of the bromines up and the fluorine down below. That's still what we use, right?
It'd be acceptable to test one. Because we don't know enough to distinguish between mirror images. Okay, and we just don't know enough. It would be acceptable. All right, let's do the next one, and we may see. Okay. We didn't answer the second question for this one. How many groups are equatorial in the best conformation? I circle it. How many groups are equatorial? Two. Okay. Because over here, only one group is equatorial. Even though it's the same exact compound. This is the same compound, it's just different conformations. Okay, over here. Let's try to get at it quicker. Now let's assess it before we even draw it. I got two chlorines. Everything here is cis. These are the same size. Once we draw it, we may see that they both can be equatorial, or maybe only one can be. If only one can be, then it's going to be a wash, and we're going to make sure this is equatorial. I think this could be a wash. I'm going to start with isopropyl. I'm going to put in equatorial. And H straight up. Okay, the chlorine is not here but here. If the isopropyl is down, how should the chlorine be? They're cis. Okay, we got an H and we got a chlorine. H straight up. Chlorine there. If you can't see because of lighting, please yell. Isopropyl and chlorine cis over there? Yes, 1-3 relationship. The next one is 1-4 to the isopropyl. Be here. How do we draw the chlorine? Straight down, yes. Everything there is cis. Is that the best?
Yes.
Yes. It actually is. Why? Because if I do a ring flip, here I have 2 equatorial and 1 axial. If I do a ring flip, what would I have?
2 axial, 1 equatorial.
2 axial, 1 equatorial. And the bigger group, which may be a little hard to distinguish, but I think the isopropyl is the biggest. That may be pretty.
It is.
That's why I kind of wanted to start with the equatorial. So that is the best. Okay? Again, I'm not worried about right hand, left hand. And how many are equatorial in the best conformation? 2. Yep. One of the chlorines is actually axial. But again, the only choice is to do a ring flip. And if you do a ring flip, you'll see that it's worse than that. You'll have larger groups more axial, and that's not as good. You want your larger groups. Okay. That's how we kind of do these. Question?
So I drew mine a bit differently. I know you said like left hand, right hand doesn't matter, right? But like I don't know if what I did was right. Maybe it's like kind of to see if it was right. Like I had my CL tutorial where he had the isopropyl, and the other one had a CL that was axial.
It's the same thing. As long as
I'd have to look at it. The question is, are the groups in a 1-3-4 relationship?
Yeah.
Are your chlorines next to each other?
Yeah.
They're 1-2. Okay. Are they all 3 below the H?
Yes.
Because all 3 below the H means they're all same size. They're all cis. I don't see how it could be wrong then, but let me look at it.
Okay.
Other than right hand, left hand question.
Quick question about the lowest energy conformation. Say we have two groups, 2 large groups that are say they're like it's in the same conformation as this question, but say the isopropyl was something different, something larger, and say that the isopropyl was was equatorial and the other two smaller groups were axial, would it still be the lowest energy if two of the smaller groups were equatorial?
Okay, what you're basically getting at is when you get multiple groups,
Mhm.
can it become hard to decide?
Yes.
Well, for Newman's, we said largest groups anti.
Mm-hmm.
Okay, you could have other groups there and you can ask a similar question. Largest groups anti. Here, I will hopefully give you a problem that's easy to see. I mean, like in the first one, the bromines either way is the same, so we had to go to another group to decide. Thus, we made sure that the other group, the F, was equatorial. Here, if you do a ring flip, you're going to see that you're then going to have only one equatorial.
Makes sense.
And that one will not be your biggest group. Does that sound as good? No. It should be clear.
Okay.
You could come up with a scenario where it's not as clear. There's also some exceptions. Do you imagine there could be?
Yes.
And a couple of problems to get at that. Is there an exception listed on this handout?
I think there was one regarding the hydrogen bonding.
Hydrogen bonding can maybe make a group want to be axial because it can have internal hydrogen bond where if it was equatorial, it could not. Yeah, there are exceptions. The homework may get at that. Or in the handouts or something. And we're going to do another 30-minute review. Yeah, class should be open on Friday. If you need to leave, go ahead, but I'm going to kind of keep on. Okay? Well, we're not quite done yet. I thought we were past time. Let's see how we can finish up to get to folks who need to leave. Okay, trying to see if we finished all the stuff. Probably on Monday, we'll kind of pull things together, first 10 minutes. Okay? We'll talk about format for tests. We'll be on Wednesday. But we will try to begin new material on Monday for test 2. Okay? Unless you want to have test on Wednesday.
No.
So instead, we'll begin test 2 material and give you another day or two. Okay. What else can we say today? Lab will be upstairs. Then after we finish lab, 4 o'clock we'll meet downstairs for lab lectures. We're meeting upstairs at 2:30. And I'll let you in like 10 minutes before, so at 2:30 we can get going. Other questions? I think got everything good? Good to go, guys? Okay. Seems like I wanted to say something else. So we'll continue with a 30-minute review. Have a good day, guys. Very strong.
So whatever, I know you bought it.
What is it? It's like broken.
It went hard on
Okay, guys. Questions?
I have a question on the quiz, the solubility, the one with the sulfur and the benzene ring versus the hydroxyl group on the cyclohexane. Is the sulfur gonna be more soluble because it's happier getting rid of that hydrogen, or like why is that one gonna be in the aqueous?
What type of compound would be in the aqueous? What type of organic compound would be in the aqueous?
I mean, my thought was like ones that can make hydrogen bonds.
No. The answer is
More polar?
ionic.
Okay. And sulfur and nitrogen.
The question is really, which one of the four will be ionic in the presence of sodium hydroxide?
Would it be the one that's most acidic?
Yes, it's the one that's most acidic, exactly.
That's what I
And that can cause the lone pairs on the orbital?
Which compound's most acidic?
Yes.
Okay.
And
How do you identify strongest acids? So we go back, you mentioned the SH compound or the OH compound. Would you rather, how do you judge acid strength to look at the conjugate base?
It's going down that one.
Which would be more stable, minus on oxygen or sulfur?
The sulfur.
Yeah. Unless there's something else going on and it becomes more difficult in assessment. But there's another reason why the sulfur there is more stable than, sulfur anion would be more stable than the oxygen anion. And you mentioned it, it's because the sulfur anion would be
Two.
Give two reasons why this SH is more acidic than the OH. One is because sulfur is larger and minus on sulfur is better than minus on oxygen. What's the other reason?
It's a conjugation, right?
Conjugation. S minus would be conjugated, but the O minus would not be. No?
I have a question, and a bit serious. You have NH2. Why isn't it NH3? Where did the hydrogen go
On the end?
to? Yes, sir.
The compound is NH2.
I thought because it lost sulfur, lost the hydrogen, it had to go somewhere.
That would be,
it would just be.
They're not interacting.
no, that would be interacting with like another.
You're thinking beyond.
The sodium hydroxide takes the H from the sulfur.
Yes, sir. Yes, sir. Tracking.
It's not going to take the H from the amino group. That's an absolute answer. Keep it relative. Is it more likely to take the H from the sulfur or the nitrogen?
The sulfur.
Yes. And that gives you your answer because
No, I took it away from the sulfur.
I underlined one. Which one? There's only one that's going to be. There's only one answer.
I got the same answer, but I mean, I got NH3 both. NH3 both, thinking between two molecules. That's what I was thinking. Should just clarify that's just NH2.
Yeah, but we got sodium hydroxide there. Sodium hydroxide is ruling everything. And sodium hydroxide is not going to allow that nitrogen. If it was NH3, sodium hydroxide would take that H and take it back to NH2 neutral. You cannot have an, NH3 would actually be an acid. NH3 plus has a pK of 10. We saw that earlier. And here's something to remember. You can't have an acid in the presence of a base. You cannot have a base in the presence of an acid. That's like reaching into a tub full of hot water and saying, I'm going to get some cold water out. You can't. If it's hot water, it's hot water. If it's basic, it's basic.
Yes, sir.
And if you combine hot and cold water,
We're gonna neutralize.
it's going to neutralize and it's going to become just tepid warm water. Once you mix them, they're going to, okay? So acids and bases is just like hot and cold water. You can have a tub full of cold water, you can have a tub full of hot, but you can't have a tub full of both. Question?
For number 4, sir, my understanding was that C was the strongest because it's sp3 hybridized, and we said that that was the most basic nitrogen. But then next would be sp2 hybridized, correct? And then the A would be sp hybridized, right? Because the lone
No.
pair.
No, that's SB2.
SB2.
It has a lone pair.
Right.
That's
So
the one where
So
for
there's
B,
three.
the lone pair is conjugating with oxygen.
and then for A, the lone pair is not conjugated with the double. Oh, because it's right next to
Yeah.
it.
Yeah,
Because
so
it
it can't
is
be a
double
PO
bonded, so there's
Okay.
just the three.
Perfect.
Yeah, so lone pair is on the B orbital, which means it's more acidic. But B is conjugating.
Keeping track of that stuff.
Yeah. So the difference in those two lone pairs is just hybridization effect. The lower nitrogen has got more S character, so it holds the electrons tighter. The orbital that the electrons are in is closer to the nucleus, closer to the molecule. Both of those have some basicity. The sp3 is more basic. sp3 nitrogens are pretty decent bases. They're not as strong as hydroxide. They're still decent bases. sp2 is a little bit less. It's marginal base. It's used as a base, but actually your body uses an sp2 nitrogen a good bit as a base, but it's fairly weak. But this here is no good. That lone pair is in a p orbital. And lone pairs in p orbitals typically not basic. Because they're busy. That lone pair is already doing something. It's bonding. It's interacting with neighboring p orbitals. Where's the neighboring p orbital?
And the oxygen.
Well, there's one here. There's also one here. I mean, there's p orbitals all over the place. That's 6. But guess what? This one's in a p orbital too. And it's interacting with all these, which just have 1. But that one is an sp2. This one's not going to move to a p orbital because there's no p orbital next door that it can interact with. The ones next door are already interacting with the current one. If there were 2 p orbitals next door and another one was like this, then maybe that lone pair could interact with one, but not as is. Did you?
Thank you.
You got it right?
Yes. Well, I understand it. Why I got it wrong.
What did you put as your answer?
Well, I take that back. I got the answer right because I recognized that C was the first, or the strongest, and that was the only one with C as the strongest. But then I thought A and B should have been reversed because I misunderstood conjugation in that the A was not sp, but rather sp2 because the double bond is not adjacent, it's actually touching the nitrogen.
Yeah. The nitrogen already has a p orbital. If it already has a p orbital, it's going to be less likely for the lone pair to move into one.
Understood.
Because the adjacent p orbitals are already interacting with the current nitrogen p orbital. So, you seem to have gotten that. So, we say the exception, but in my exception when I wrote it, I said as long as the next door, it can interact with the next door p orbital. And that's what's going on here. In this case, it can't. This nitrogen is just like this nitrogen. These two nitrogens are identical. But this nitrogen's different. So this nitrogen is more like the B nitrogen. That lone pair is in a p orbital. That lone pair is in sp2. And there are commonly two types of nitrogens. Like that. There's more, but those are the two that's most often kind of considered. Architecture of organic compounds, particularly heteroatoms with lone pairs. Other questions?
Yes, sir. I have a question. It's on that. For IR, I could easily, when looking at the spectra, I could easily identify like the CC bonds or the OH region. But I'm having issues translating that to an actual molecule. So I'll be able to identify the molecule. I could look at the graph and tell this is OH region, this is a CC, this is a triple bond region. But how do I translate that to the molecule? I'm having issues translating that to like.
Do you have a problem that you're looking at?
On like page 34, on this 1B.
Which one?
Number 1B.
What's the question?
Okay, I could identify the regions like the CO bonds and a little bit of CH bonds, but how do I translate that to actually identify molecule?
Oh.
Not quite certain of your question, but I'll do this here. I have magical 3000 line, yeah?
Yeah, the 3000 and the...
It looks like I have both sp3CH
Yes, sir.
and sp2CH.
Yes, sir.
There doesn't appear to be an OH or NH, which I thought that's what you were asking about.
No, this I can see the CO part.
Carbonyl?
Yeah, I can see the carbonyl.
Pretty strong peak here. It's a little low in terms of weight number. What is the value? Can we see here? Readable? This here, the more you come down, that's 150, 0. The stronger the peak comes down, the lower the number will be the second number. This is like the intensity of the peak. Peak position and then intensity. Lower number means it came down further. This comes down real far. I think that's the 1667. Is that? Or is it 57? 1667.
Yes, sir, that's what I see.
That looks like a carbonyl. It's fairly low.
I could identify all of that. Now, how do I translate that information into...
Getting the answer?
Yes, sir.
Well, the answer's up there.
Well, we know that.
If I didn't give you any choices, you couldn't.
No, but yeah.
Okay, but the answer's up there. We just need to, well, let's do it. We just need to eliminate.
You're looking for those things.
For example, can it be this one here?
No.
No, because this doesn't contain sp2CH. Well, it contains an aldehyde, but aldehyde's in a very unique position. And you should know that position. Over here, could it be this one? No, there's no sp2CH. Can it be that one? No, no sp2CH. Those three don't contain that. You got to trust this information around 3000. Okay. Can it be this one? No, there's no NH down here in the OH-NH region. Not that one. Can it be this one?
Yes. Oh no, because it doesn't have an SP.
It has both of these.
There's no
Carbonyl.
the CL.
Yeah, so the
Did we talk about carbonyl positioning?
the CO carbonyl is going to be high, right?
CO carbonyl is high. That's called acid chloride. It's typically more like 1800. So low carbonyl. Low carbonyl is very often amide. Look at your carbonyl differences. Amides typically have a low. Ketones, esters, aldehydes, those are sort of mid-range, although ester may be a little bit high. This could be a ketone if it was conjugated, but that's an advanced consideration. In organic 2, we look back again at carbonyl positioning. So it's worth learning now. My first thought is it looks like an amide that has both of these, and there's no NH or OH.
Professor, also don't we know that it most likely has a ring because of the mountain range?
Aromatic, yes. It's got a little aromatic, a little weak, but it looks like an aromatic, and it's also got some through here, 15, 1600. Who was in lab yesterday afternoon? Lab lecture. Lab lecture yesterday?
I think we'll have it on Friday.
Do it?
I think we all have it on Friday.
Yeah, today.
Yeah. I would think that some of the other folks were here, but that's, reckon not.
Oh, you said double bonds are at 1500, right?
Look, you got the IR table in the handout. Look near the bottom. It says alkene or CC double bond, it says.
Right.
IR handout. The table, it's got the big E at the top right.
Yeah, I think that's...
Look near the bottom. CC double bond. Doesn't it say arene or aryl?
Yeah, and their reads are 1600, 1500.
1600, 1500. Okay? 1500, 1600. You get a couple of peaks in there for the carbon-carbon double bonds of the benzene ring. Between there and here, yes, you can tell it looks aromatic ring. And the most common is a benzene ring. So yes, it does look aromatic, and thus, to me, that's something you can start with. The answer is on the top row.
So you're looking for a benzene ring with an amide and a carbonyl group.
Which handout are you looking
A
at?
benzene ring with a carbonyl that's likely an amide. There's no NH though. Very importantly, there's no NH. So which one is it? It looks like the answer is what?
A.
I think it's A. Is that right?
Yes, sir.
Okay. Did that answer your question?
Yes, sir. So chlorine identified the regions that do process of elimination.
I just have a hard time
I said,
understanding.
what we do is identify the regions, then do process of elimination to start to get the answers.
Yeah, start looking at what structures are provided and rule them out.
Yes, sir. That should make things easier.
And hopefully you'll be able to rule out every one but one.
Yes, sir.
And that's more test-taking strategy because of the way the question is presented to you.
Yes, sir.
Can we look at the last
And
one?
one other thing is, if you narrow it down to 2, you also have other spectra on the page. Maybe one of those 2 you see goes with another spectrum. But if you assign that one down here, then you say, well, then the other one must be this one. Another test-taking strategy. All right? So don't like just sit here for 10 minutes. If you're having a little difficult, move to the other ones. Okay?
Yes, sir.
Can we look at the last one on this page? Because it was really close. I picked D, but the answer is actually E.
Okay. Down here at the bottom?
Yeah, the 4B.
And you picked which one?
D?
David?
Yeah, and the answer is actually E. So the only difference is that hydrogen.
Okay, one's an aldehyde. Okay. Key difference is aldehyde. Look at your table with the E on it. Aldehyde. What does it tell you about aldehyde? You have the carbonyl, but you also have the CH of the aldehyde. And what?
That weird, like, there's a really long one, and then there's like another little peak in there, and then you're...
Now the CH of an aldehyde is an sp2CH. But it doesn't occur just above 3,000 like most of them do. That sp2CH of an aldehyde is unique, and it occurs where? Below 3,000 at about 2750, 2850. Is that right from the table?
2830 to 2700.
Okay. I say 2750, 2850. That is a little bit more to the right than sp3ch, which is more like 2950. Okay? And that right here is your aldehyde CH. Because if you draw the 3000 line, you see how that's a little bit more to the right of the 3000 line? Usually sp3ch is right up against it. You see how this is more up against it? It's very close. You can also, though, look at your numbers here. What is that, 27? Okay. Can you read that on your in the book? It's hard, maybe hard to read here.
2738?
Yeah, it's a little tricky, but yeah, it looks like 27. It looks like 27.
Yeah. 20, a fairly strong peak at 27 something. You're not going to get that for the ketone. It would be more like 29 something for the sp3. Okay. So the aldehyde CH. Otherwise, yes. Otherwise, distinguishing between D and E is quite difficult. Now, between D and I, that's easier because D is aromatic and I is not. And D and C is kind of easy based on carbonyl position. Acid chloride, high carbonyl, 1800. This is going to be more like 1700. Acid chlorides, high carbonyl, amides, low carbonyl. The others are sort of mid-range. Is that what the table says? Can I look? The one below acid chloride with the RCO2O, that's an anhydride. We don't know that one yet. You'll see that in organic 2. Ester aldehyde, good. You have them written here. Those are condensed. Conjugation does lower carbonyl. We'll mention that more specifically in organic 2. Yes, high, standard, low. Very good. The ester is a little bit high, but I would still call it standard. Because if you see a carbonyl about 1740, it's probably an ester. Because aldehydes and ketones are probably not 1740. Okay? So the carbonyl positioning. Now, some faculty may not ask you to look at that. I think it's useful. It's extra information, but I think it's extra information that will help you solve problems easily. Okay? Because if you just say carbonyl is a carbonyl, carbonyl, you're missing out on some information that you but again, with IR, there's often multiple things you can look at. But sometimes you get down to where it's got to be one specific thing, and here the aldehyde. We got it?
Yep.
Next question?
7, number 2E. Picture 7, number 2E. What affects the deepness of the OH bond?
What page?
37, number 2E. Looking at it, you think it's C because there's an OH and aromatic rings. So my question is, what's affecting the thickness of the OH curve?
This does look like an OH.
Yes, sir.
Very intense, broad. sp2, sp3ch.
Yes, sir. And aromatic rings?
Um, 15. I don't know what, that's kind of odd.
Yeah, and then overtone or aromatic rings.
It's a little odd. This almost does not look aromatic. You sure it's aromatic?
I haven't checked the answers, but when you look at it and compared to what's provided, I'm thinking more of C as being the answer.
Oh, and it's got double bonds.
The only other option would be
Does this have a carbonyl?
No.
No carbonyl. It looks like it's an alcohol.
Yeah,
It has to be C.
Yeah.
Okay. See, now that I'm looking at the answers, I can tell it's, okay, it must be an aromatic. Because it's not this. Why is it not that?
Because there's the aromatic, the melting range for the aromatic ring.
Because that one does not contain sp2ch. But the magical line showed us there was something above it. That does not contain sp2ch, and amine is not going to be that intense anyway. There's no carbonyl, there's no OH or NH. There's no carbonyl, no carbonyl, no carbonyl. There's no cyano group at 2200. There's no two peaks in the NH region. There's no carbonyl, there's no carbonyl. It looks like it's C.
Right, sir.
And indeed, it must be aromatic. It just looked a little odd. It wasn't as...
Was there an answer about the depth of the OH bond?
Yeah, like what affects how deep it, how deep the OH bond?
OHs are classically very intense and like that. Upstairs on that instrument, it's going to be weaker. Modern instruments are weaker with the OH because it's really the light is not passing through the sample anymore. Instead, it's coming off and coming up to that eye and bouncing off of it. Because of that, the peaks to the left in the IR are weaker. If you go back to the old method, you can get a more traditional textbook looking IR. But your prep is going to be, instead of just putting a compound up there, it's going to take you 10 minutes to do it. Okay. So for high throughput,
It's not going to be a C. It's still going to be that's fine.
but textbooks are still going to show the classical old OH peak. You know, maybe in 10 or 20 years that's going to change in textbooks.
I have a quick question on that page. For 4E, there's like a little bump to start with. Would that be like overtone? The very first little squiggly.
Here,
Right.
possibly overtone.
Okay.
It's pretty darn weak and skewed a little bit. Otherwise, what do you think it might be? NH?
Yeah.
No. But it's, I just thought it wasn't strong enough.
Yeah. Again, though, if you think it's an NH, you can always put a question mark, and then you say, okay. Then you go looking at a compound, and And maybe you have a compound that has all of this and it doesn't have an NH. Then you say, well, maybe that's it and this is really not an NH peak. If you did not have any compounds to look at, you would just have to say, perhaps it's NH, and that's all you can tell. And you need more information somewhere to answer that.
Well, why would you say NH over OH for that one?
But OH is going
OH
to,
is very strong.
Oh, okay.
even upstairs, OH is going to be something.
Okay.
Sometimes NHs can be weak,
Okay.
particularly if they're not conjugated. Conjugation makes the NH stronger. And this should have been discussed in the video and in the handout. So look at examples. Sometimes an NH can be pretty darn small, but if it's conjugated, it'll be stronger. Conjugation typically increases the NH. That's why an amide NH or an aniline NH is stronger. Look at the handout if you want to see. I think there's two examples.
Can a NH peak be like really broad?
It can be, but usually the OH tends to be broader. Hydrogen bonding broadens it out. And the less it does hydrogen bonding, the sharper it will be. What type of NH is going to do less hydrogen bonding? One in which the lone pair is conjugated. If the lone pair is conjugated, it ain't going to do as much of being a base or hydrogen bonding. So a conjugated with the lone pair is conjugated, cuts down on hydrogen bonding, and it makes the peak a little sharper. More precise. Hydrogen bonding brings in neighbors and stuff, and it broadens things out.
What's the page? I mean, what's the page? Just 33, 33A, but it's not late.
Yeah, 33.
4, E. F. It says F. Oh, okay, okay.
So the OH?
She says that there's, or he says that there's no NH bond on 4E, so it can't just be, so it has to be F.
Right.
For number 2 on the quiz, it's basically just asking what predominates. So, I understand the rule about if the pH is greater than the pKa, right, the base will predominate. But then as far as I get the pK of is 7 for the SH, but then what do we do about the H2N? Do we have to worry about that at all? So I get that the sulfur loses the hydrogen, right?
Well, we did. We answered this. The answer is it's going to be, that would be the form. We didn't worry about it, but the answer ended up being identical as
I
where.
asked a question.
Oh, you
Because it looks like it's gonna be hydrogen.
right.
Yeah.
Okay.
Well, it says right there at the base, so I'm gonna have to leave that space. What? Space. Space. Yeah, so just use that. That's what I'm wondering, like, where's the hydrogen?
When you see a means of 10, around 10, it's acting as a base.
Right.
Because if it's acting as an acid, how acidic is that? How likely is that to act as an acid?
Not likely.
It actually is not likely because nitrogen, even though it's more electronegative than carbon, it's not as electronegative as oxygen or Cl or something. And so the pKa of that acting as an acid is more like 30. Again, I showed you that in the table. But I clarified that acting as a, thus if it acts as a base, it becomes what if it acts as a base?
Right. That's why I'm confused. Why there's no. So, right. Why there's there no NH3 in the predominating form? Because it's
Okay, well let's get there because which is the A form, right or left?
I don't understand your question.
You either have an A form or a B form, and then there's an also the acidic form or the basic form.
Oh, okay.
Which is the acidic form?
It's a,
Left.
The acidic form is the species that has the H. Which one
Right.
has the H?
NH3.
oh,
That's the acidic form, that's the basic form. Which will predominate in this question?
The basic form. Because we have pH.
The thing that can vary is above the constant. 12 is above the constant. So the basic side, which side will predominate then?
B. Or the H2N.
The basic form, circle. And circle is, that's how I have it drawn over there in the answer.
Okay.
Exactly as circle.
Understood.
At what pH will the NH3 positive predominate?
12. And that'd be.
Not at 12. At 12, B predominates. At what pH?
Oh wait, what pH? Oh.
At what pH will the NH3 positive predominate? The acidic
pH
form.
4, pH 2.
Many pHs, but at below 10. So if you dissolve this compound up and adjust the pH to 5,
The NH3 would dominate.
NH3 would be, the nitrogen would be protonated, we say. At pH of 5, how is the SH going to exist?
Acid is?
Acid form. What is the acid form?
Right now.
Where it is right now.
As shown, SH, yes. So you have to know what the A and B forms look like. And when the pH is greater than the pKa, the B form predominates. And when the pH is less than the pKa, the A form predominates. What predominates if pH equals pKa?
None.
Neither. It's a 1-to-1 ratio.
Yeah.
Because log of 1 is 0. And if that is 0, the other two equal each other. Flip that around, the other two only equal each other when the other term is 0. And the other term is only 0 when they equal each other. When they equal each other. And thus, if they equal each other, that means you have a perfect equilibrium, 50-50. How do you get a pH of 12?
Add a lot of base.
Maybe that's, to adjust pH, if you just took that compound and dissolved it in water, it's going to take on its own pH. And that's called something else, like, okay. You then adjust pHs by adding base to the base. To get to pH of 12, base had to be added.
Yeah, add a lot of base.
But when you add that base, guess what? It's going to remove this H and turn that to death. But it ain't going to remove one of these. Not an aqueous base. Hopefully that makes sense. Another question, which is more acidic, SH or NH?
SH?
SH. That's why the base, when it's added to adjust the pH, removes the SH, but not the other one. Now, it could be that it could remove both. But in this example, it only removes that one because amines are not that acidic. Okay, there's many layers of how you want to get into that. In the end, being able to do the problems with the also above. And the amines do throw a little curveball in there because we don't use PKBs. pKa of an amine usually refers to the conjugate acid. Question?
For the first one, which side of the equilibrium is favored?
The product.
Oh, we didn't do that. Which side is favored?
The brightness side, because of the lower pKa.
What's the acid over here? The thing with the H. 10. What's the acid over here? The thing with the H. Doesn't that now have the H?
Yeah.
What's its pKa?
7.
7. Which is favored, 10 or 7?
7.
10.
No, the lower pKa.
The
No,
weaker,
higher
the weaker
pKa.
acid's favored. So the
Weaker acid is favored.
the reaction.
This side is actually favored.
Base.
Thus, is that base strong enough to fully deprotonate that phenol?
No.
It's not. If your job was to come up with a base that will convert the phenol to the anion over there, and if you chose that base, that would not be a good choice. It's not strong enough. That doesn't mean we can't show an acid-base reaction that would be most likely to occur. Is there any other acid-base reaction that would be more likely than the one we showed? I mean, do you want to use a different base? No, we used the strongest base on the board. Do you want to go for a different H? No, we found the most acidic H on the board, and we reacted those. But guess what? The equilibrium is not favorable here. For this to be favored, the pKa of your base needs to be higher or lower?
If it's a higher pKa, then you're going to end up, your conjugate base is going to be stronger.
Well,
Or your conjugate acid of your base is going to be stronger, right? If your pKa of your base is higher than the conjugate.
the conjugate acid would be weaker.
No, we need it lower.
So you need a pK of like 11 or 12, and then that would make it a weaker
Yeah.
acid on the right side.
If this equals 12 for the base, then you would write 12 over here. If you wrote 12 over here, which is
That's right,
favored,
weak
10 or
acid.
12?
12.
Yeah. You need a pKa. The base needs to be higher than that. Don't memorize that, but just be able to assess that. Try to memorize these things, you're going to get all like... Well, if that's 12, that really means this is 12, isn't it?
Yeah.
Okay? You really need a stronger base. Do you know of any base that has a pKa up around 12 or even higher?
And sodium hydroxide? Sodium hydroxide?
Yes, hydroxide.
Like 60.
What's the pKa of hydroxide?
16, 17?
About 16, which if this is acting as a base, the 16 refers to what?
The conjugate acid?
What's the conjugate acid?
HO, water.
Water. Haven't we said the pKa of water is about 16? Okay. If this was hydroxide, you would have 16, but you would put it over here because you'd form water. And which is favored, 10 or 16?
16.
16. Hydroxide would be strong enough to do it. And we saw another base right here that would be strong enough. Guanidine circle is a pK of 12. That would be strong enough to do that we're looking at. But the base given is weaker. That's 7. That means this is 7. Weaker base. Which is a stronger acid, 12 or 7?
7.
7. Weaker base, stronger conjugate acid. So all these things lead back to the same answer. However you want to. These terms, these things you've been told, they're all there. Sorting them out and figure out what you want to use to get your answer. They don't all have to be used. They all mean the same thing. That's what you have to sort out.
For one, we chose that particular O because of conjugation, and resonance is not applicable, correct?
Which one?
For number 1, we chose the particular O that we chose because of conjugation only, correct?
And what'd you say?
For number 1,
I heard that, but then you said
the O that we chose was due to conjugation, correct? Exclusively, not resonance.
no. I thought that's what you
Oh,
said. Conjugation and resonance is the same thing.
I think you think about the inductive effects, on the
so the OH axial OH, the lone pairs are conjugated across the p orbital, but as far as resonance, we couldn't redraw the structure another way, right?
Sure you can. Resonance and conjugation is the same thing.
Because we couldn't put a double bond on the O and the carbon because then carbon would have too many bonds.
No, but when you do that, you would move the carbon-carbon double bond.
Okay, clear.
We haven't done much resonance structures. We'll do that more during test 3.
But you did say resonance is just p orbital overlap.
Yeah.
Right, okay.
The difference between the two in terms of how you use the terms is conjugation is more of, I think, looking at the hybrid or the true structure. The orbitals are all conjugated.
Okay.
But that's also resonant. But when I use the term resonance, then I'm starting to draw the individual resonance structures.
Right.
But it's really all the same thing. The individual resonance structures is just 2 or 3 fake structures of the whole thing. But it's the same. Yes. Whenever you have conjugation, I think this is right. It has to be. Whenever you have conjugation, you're always going to be able to draw resonance structures. So it's the same. It's the same thing.
Understood.
It's just sometimes you use one word. It's conjugated. It's resonancy localized. It's just okay. Some people say one thing. Last question.